Hi, so in this video, we'll look at a counting argument. So the situation is that we have a list, just like we have in the Grover search. So we have a list, and there are certain elements that are marked over here. There are n elements and items in the list, and the number of marked elements is m. And this is unknown. And our goal is to find a classical algorithm that finds this m. Now, a straightforward deterministic algorithm is to just go through the list and just check if the element is marked and keep a count of the number of marked elements. And that's a straightforward algorithm. And you know that this will take uh, n searches to the database or n queries to the database. Now, can we do better by maybe going via probabilistic method, right? And in this explanation, in this video, we show that we can't do better than order n queries to the database if we want the estimate to high accuracy. Okay, so we show that if we want an accurate estimate of m with high probability, then we need order of n queries. So basically, we can't do better than order n queries, even using a randomized method. Now, in the next video, we're going to show that this queries can be reduced to square root of n by using a quantum algorithm, which is based on phase estimation. Okay, so in this video, let's see how we can get to this estimate. So the first thing we are going to do is to find a randomized procedure to estimate m. And the way to do it is quite straightforward. We choose, so the procedure is the following. Well, randomly choose k elements from the database. Okay. And we let xi, which we define the random variable xi equal to 1 if the ith chosen item is marked and 0 else. And then we set the estimator. So this m hat will be our estimator of m. We'll take this to be summation xi over k into n, right? And this will be our estimate of m. Now, why is this a good estimate? Because if you just go logically, then summation xi over n will be just approximately equal to m over n. This will be the proportion of marked elements. And into n, this will be m, as long as we choose k large enough. Now, how large should k be? And that's what we are going to show, that it has to be at least of order n if I want to get a accurate estimate. Now, a couple of things. So we look at expectation of this random variable m hat, and using linearity of expectation. So we'll get this to be n over k times summation I equal to 1 to k expectation of xi. This is due to linearity of expectation. What is expectation of xi? Well, xi is a 0, 1 random variable. So 0, 1, this is xi. And probability of getting a marked element is m over n. Probability of not getting a marked element is 1 minus m over n. So expectation of xi is just m over n. And using our knowledge of Bernoulli random variables, variance is xi is m over n into 1 minus m over n. Okay, so therefore, we get expectation of m hat to be n over k into k times m over n. So this will be equal to m. So our estimator of m is, whenever expectation of the estimator is equal to the parameter to be estimated, then we say that it's an unbiased estimator. And variance of m hat will be n. So we can use the fact that variance of, if I have a sum of independent random variables, then the variance adds up, and variance of a times x is a square variance of x. So if we use that, then we'll get variance of is equal to n square over k square into k times variance of xi. And substituting this over here, we'll get variance of m hat is equal to n square over k square into k into m over n into 1 minus m over n. And this simplifies to m into n minus m over k. Okay, so we have an estimator of our unknown parameter m, and we have the expectation of m hat, and the variance is known. Now, the next step is to show you, okay, so what do we need over here? Okay, so let's look at this. So we want to show that we want to get an accurate estimate of m. So what does accurate mean? So in our case, we'll say that accuracy means that our estimate is within square root of m. So this is m plus square root of m and m minus square root of m. So we'll say that our estimate of m will be within this interval. And we have also said with high probability. So our probability will be greater than or equal to 3 over 4. So if we use these two parameters, then we can use an inequality called the Chebyshev's inequality. So let's look at so Chebyshev's inequality is the following. Chebyshev's inequality. If I have a random variable with mean mu x and variance sigma square x, so let's say we have the probability of x minus mu of x greater than a is less than sigma x square over a square. So this is the Chebyshev inequality where mu x is the expectation of x and sigma x square is the variance. So this is expectation of x is equal to mu x. This is variance of x. Okay. So in our case, we'll take x is equal to m hat. Mu x we know equal to m. And a we'll take as a is equal to square root of m. Okay. So what we want to know is that what is the probability that our random variable, so this is mu of m hat, and this is, so mu of m hat is just m. So this is m, and this is m plus square root of m, and this is m minus square root of m. And this Chebyshev's inequality says that, okay, what is the probability that this estimate is away from the interval that we need? And it says that it goes down as um, a, uh, quadratically, right? So now if I substitute all the values over here, I'll get m hat minus m. This is because expectation of m hat is m itself, greater than equal to square root of m is less than. Now I have to substitute the variance of m hat, which is we calculate to be n into n minus m over k. And then a square is sigma square root of m square, right? So this is, we'll get probability of m hat minus m greater than square root of m is less than um, n minus m over k into m. So this is, sorry, this is m over here. Yeah. Right. So this will be equal to n minus m over k. Now, if I flip this inequality, if I take the complement of this event, then I'll get probability of m hat minus m less than or equal to square root of m is greater than 1 minus n minus m over k. Okay. So I'm just using the complement of the event over here and changing the inequalities. And okay, so now we want this probability to be greater than 3 over 4. Suppose I take this value. So how large should k be? So if I substitute this, if I take this to be greater than 3 over 4, right? Then if I want this to be greater than 3 over 4, then I'll have to solve this inequality to figure out how large k must be. And I'm going to use an approximation that m is much smaller than n. Then basically I'll get 1 minus, so I'm going to use this approximation to be just n, where k is greater than 3 over 4. And which, if I solve this, I'll get k to be greater than 4n, which is of order n. Okay, so the upshot is that if I use the randomized procedure to estimate n to within square root of m, then to get this estimate with high probability, and we have chosen a number to be 3 over 4, we'll have to make n queries to the, at least n queries to the database. Okay, so that's the main argument. Thank you.